So let's start with different ways of using a laser scanner. For instance, an aerial laser scanner is a device that is set on a plane, and then this active sensor, it measures vertically. You can also put a laser scanner on a car, then it's mobile scanning. Then you have short-range laser scanner. They have a range usually around 300 meters. That's what we will be working with. And then you have also long-range laser scanner that you can place on higher points, so you can scan larger landscapes. There are some scanners that go until 6 kilometers. What you get as a result is shown down here as a section through a tropical canopy. You can recognize the different elements that constitute this landscape. You clearly see the terrain, a small infrastructure like a bench, maybe a deposit of earth. You can actually recognize different tree types. There's a palm tree here, and all the different tropical species that compose this tiny forest. So this geometric documentation is a point cloud model made of millions of points. We'll be using a software that is called CloudCompare in this course, and which opens all sorts of point cloud models. When you open CloudCompare and look at the file types, you see a long list. I think that's not even the full list. And we'll be using some specific point clouds. And here I framed those who are most current. There is the native format of CloudCompare, which is a bin format. It's the one that you will be using to store the project temporarily. It's not an exchange format because it's only used by CloudCompare. So you need to use other formats to exchange with other software. Then the second one is a ASCII cloud. It's just a text-based file. And if you follow the dots here, you see actually how this text file works. It's actually an Excel table. So you have columns and rows. And the first three columns are X, Y, Z. Then you can, for instance, have other columns that are the RGB data for colors or Scala fields. Then you have other formats like LAS or LAZ format. This is the one that we'll be using to store, to save the point cloud. It's the most compact, and it's also the standard to exchange point cloud models. And the LAZ format, the difference between LAS and LAZ is just that the LAZ is more compressed, it's zipped, but both have pretty much the same specification structure. What we'll be doing today also, we'll be showing you how to interact with such a point cloud model and direct ways to actually segment the point cloud model. I have a few examples here. This is a hospital in Damascus, and here you see simply how sections are animated through this building. You can do the same at larger scale. Here we are looking at a real point cloud scan along the lakeshore of Lake Geneva. We see the whole terracing, how the buildings are set on the topography, and of course also how the trees are planted. And those are the different ways of how to realize segmentation. You can manually segment the point cloud model. So in CloudCompare, you just create a selection and you cut out the model based on this selection. Then you can use the section tool, which is a box, and you just move around the sections. Then you can filter the point cloud model based on semantic values. So semantics is just a classification. This comes usually pre-prepared in the data sets we get in Switzerland. You have different classes to just separate the elements. So I can filter out the trees or all sorts of elements. Then you say, for instance, I want to filter only a certain height, and you can extract it. So that's the filter idea. Or you can segment by components. Here are a few examples. If you have a mountain peak or an island, you can just cut whatever is lower. You can create sections here. You just extract a 10-meter width line, or you filter by elevation, or you can filter out manually certain elements that you want to highlight. Point cloud models that are distributed usually contain georeference. This is also the case on the dataset we'll be using today. So they are already geolocated in space and usually refer to a certain projection grid. When we scan with a terrestrial laser scanner, we are not working in a georeference. What we can do, though, is to then combine the two data sets. So we'll be using something that is called registration, which means you connect a data set onto another data set. Practically, you can combine very precisely the data set, and you can give this georeference of one data set to the other data set. So we can position our terrestrial laser scan within a geographic grid. In Switzerland, the geographic coordination system is called Landesvermessung 95. They separate the north and east coordinates by putting a different first number. So north coordinates always start with a 1 and the east always with a 2. There's actually a good movie that I would recommend, Schweizer Koordinatensystem. It will just explain the general principles of how this works. So we have a global coordinate system made of latitude and longitudes. And then we have the local Swiss system. Every country uses their own official coordinate system. Usually it is in meters. And the projection means that usually the map is projected, rolled out on a cylinder. Every country is using their own system, which optimizes that projection for their own geography. When we work with this data set, the coordinates are very big. It's 2 million and 1 million meters. The trick is to temporarily shift that data set closest to the zero of the software. CloudCompare has this already as an automatic process. When you load a geographic located data set into CloudCompare, it will automatically open a window that proposes a geoshift. And again, the geoshift is just a temporary measure. As soon as you save again the data set, it will add again the shift. What I suggest is always to use the same shift, because then if you combine different elements, they all have the same geoshift. And the best way to do that is to round off the data set with 4 zeros. In Switzerland, there are download platforms. In this case, you have a screenshot from Swiss Topo, where you can select these tiles. For instance, you draw a selection mark, and then you download the selection as a zipped file. We'll be using the Zurich Canton platform because they have a slightly more detailed aerial scan of Zurich. The last thing that I would like to show, and this goes in a little bit into this mapping exercise that I would like to do with you. On the point cloud model, you can also visualize scientifically the data. So you will use different color hues to highlight certain properties. Here's an example. You can represent the height simply by coloring, in this case, the whole alpine range from 420 meters to 2,500 meters. And then you actually start seeing the relationships of the lower and higher valleys and peaks. You can do this at different scales. So at the very small scale, this is a LiDAR taken in the Philippines. You see actually volcanic shapes, and next to it, rice fields and a river system. You can zoom out to the entire Beemster polder, one of the oldest polders in the Netherlands. And you see actually that the polder is slightly lower than the surrounding land. So you can be very specific about how the few meters difference create the landscape. Or you can zoom at a city level, and here Sao Paulo on a mountain ridge. So you have the main avenue, the Avenida Paulista, and the whole city then expanded around it. So it's really a spatial representation of these elements. So what I just showed you is actually a topographic height. The topographic height is always the geodesic dome around the globe. It's not a perfect sphere. It actually depends on gravity. You can imagine that the dotted line is simply the zero level of the ocean, would there be ocean in that very point. So sometimes it's lower because of gravity, sometimes it's higher, but this is the reference level where the elevation is measured about. And so what does it tell us? Here you see actually two maps of the Mississippi River. This is a historic map by Harold Finsk, and you see the Mississippi River that he surveyed and he drew. But with the LiDAR technology that we have today, we can do exactly the same just by narrowing the elevation range. In this case, the white values are lower and the black values are higher. And you see the whole topography and how the river actually transformed the landscape. Then we incline the reference. And this means that you look, for instance, at the topographic variation. Here we have the Piano Magadino. This is the Ticino Valley. So here's Bellinzona. And if we incline the plane, aligning it a bit along the valley, we can see actually also meanders. We can have a different variation where, for instance, we align the reference directly to the topography. So the topography, it's its own reference. And this is a declivity map. It's just indicating the slope. Or we compare objects on top of the topography, and then I have a house, or in this case, a forest, and I represent the forest by heights. So I can visualize what trees are biggest or what is the formation of this forest. So the idea is not to map only its own values, but also combine different properties. And I will be sending out a mail where you can add on an Excel sheet the maps that you would like to choose. There are many maps that you can choose from the GIS platform of the Canton of Zurich, and then you will just project that map onto your point cloud. Last time I said that there could be two sites of investigation, but since we're a smaller group, I think it makes absolutely sense to reduce it only on one case study site. And I would like to take this one because it's more accessible. So it will be easier for us when we use the laser scanners